Hello everyone, welcome back to the NPTEL course on materials informatics. In today's lecture we will talk about neural networks. So just as a recap, in the last lecture we covered some more of the classical machine learning models which have slightly more complication compared to simple linear regression, support vector machines and so on. So we basically looked at ensemble models which can do classification and regression tasks as well, and we basically looked at the example of random forest, and the main principle behind these ensemble models is that it uses independent diverse weak learners to create a strong prediction or a strong learning. We also looked at various aspects associated with ensemble methods in terms of how you split your data while creating ensemble models, and also whether you learn sequentially or parallelly. So the thing to note about random forest is it has a lot of additional hyperparameters compared to simpler models, and apart from ensemble models we also looked at models to reduce dimensionality of a given problem. So where the key idea is to reduce the number of features to ensure that our sort of machine learning model is more tractable. We basically looked at two types of dimensionality reduction. One is what is referred to as projection learning, the other is what is referred to as manifold learning. We also looked at a few hyperparameters associated with dimensionality reduction. So in this lecture we will complicate things a little more by going into the realm of neural networks, and as with before, all the schematics that I am going to be using in this lecture are from this book by Aurélien Geron unless otherwise mentioned. Okay. So the idea of artificial neural networks is not very recent. So in fact the idea of artificial neurons were introduced back in 1943, and these were basically inspired from biological neurons. So as most of you are aware, our brains are a collection of neurons. So neurons are the individual cells. Each neuron is actually connected to other neurons, and they send across short electrical impulses across these across the different neurons. So depending on the magnitude of the impulse that a neuron receives, it either gets activated or it does not get activated, and depending on which collection of neurons get activated, our brain sort of learns or performs a certain task. So that is how biological neurons sort of in a very basic sense work. And artificial neurons as proposed in 1943 were of the similar idea as well, right. So one can perform various logical operation with the collection of these artificial neurons. So for example, let us say you have two neurons here with one neuron sort of connected to the output of one neuron feeding to both the neurons, both the inputs of your neuron C. Then this is basically equivalent to creating an equality or a duplication operation. So whatever is the response of neuron A will be the same as neuron C. So this is the simplest logical operation that we can think of. So where neuron sort of duplicates itself. We can also think of AND connection. So basically if you think about this connection, right. So if both A and B are sort of active, then C becomes active. If either of them are inactive, then it is not active anymore. So this is an example of a simple AND connection. In the case of an OR connection, we create more sort of inputs here. So the output of A sort of doubles as an input, and the input of B also doubles. So as long as at least two out of these four inputs are 1, C is going to output a value of 1 here. So this is basically equivalent to an OR operation, because the A's output is sort of doubled, so it feeds into 2 input nodes here, and same is the case of B. So this is a very simple example of an OR operation, and we can also create a NOT operation where we have a negation operator here to the output of B. So so A is always active here. So depending on the output of B, you either you get the opposite value. So B is 0, you get a value of 1. If B is 1, you get a value of 0. Right. So we can create these types of artificial collection of neurons which can perform simple logical operations, right. And if you create more complicated networks, so these connections of neurons are fairly simple, right. So you just have 2 or 3 neurons connected sequentially, and they perform one simple mathematical or logical operation. If we create a network of artificial neurons, a more complicated network, then that network is what is referred to as artificial neural network or ANN. So, artificial neural networks or at least artificial neurons as an idea is not very recent, it has existed for almost 80 years now, and artificial neural networks is a simple sort of extension of the connections between artificial neurons themselves. Alright. Let us now move to the idea behind what is referred to as perceptron. So, the perceptron as a sort of a model, a neural network based model was introduced in 1957. Perceptrons are also called threshold logic units. They are called threshold logic units because whatever output they give out depends on a certain threshold function. So, if the amount of inputs that your perceptron is receiving is above this threshold, then the output is true. If it is below a certain threshold, then the output is false, right. So, very basically how a perceptron works is that it receives multiple inputs. So, x1, x2, x3 are your inputs here. The inputs can be weighted with different values. So, x1 can have a corresponding weight assigned to it, x2 can have corresponding weight assigned to it, and x3 can have a weight corresponding to it. These weights are basically dictating how important these inputs are. So, for example, in the problem of predicting housing prices, right, if x1 is income, and let us say we consider income to be a very important input, then we assign a higher weight for that income, right, and same thing with x2, x3 and so on. The net inputs that your perceptron receives are basically the weight times your original input. So, this would be w1 times x1, w2 times x2 and w3 times x3, right, and we typically do a simple summation of these inputs, and as long as the summation of the various inputs is above a certain threshold, then the output is 1, and if it is below a certain threshold, then the output is 0, right. So, we sort of denote weight sum as this quantity here, right. So, it is a summation of x transpose times your weights, and this threshold function is usually a step function. We can also call this as a Heaviside function, right. So, if your input is let us say if you imagine this as a value of x versus y. So, it is a graph of x versus y. If x is less than 0, then your step function returns a value of 0. If x is greater than 0, then it returns a value of 1, right, or it can have a different threshold also. So, the threshold is something that we have to set or the model has to learn by itself, right. So, the net output of the model is basically this step function, right, whatever the step function we use and its operation on the net inputs that we get, right. So, this is the net output of the model, and the way this model works is it actually learns all of the weights. So, you basically try to feed in the different inputs, you start predicting an output, and then you train this output with respect to a target, and in order to minimize the errors against the target, you tune the weights accordingly, right. So, the idea is to sort of tune the weights such that we get the output that we desire. So, this is in a very simple sense how a perceptron works, and if you think about modern day artificial neural networks, they are basically a collection of different perceptrons, right. So, different perceptrons, what kind of activation functions they use, how are their inputs connected, how are they weighted, right, and also how dense the connections are between the different perceptrons, right. And the other sort of nice thing to note about perceptron is that it can very easily perform a multi-class classification. So, if you take an isolated perceptron, it is very easy to visualize that it can perform a binary classification, so either a 0 or a 1, but you can very easily change this output. So, you can introduce some kind of a softmax function here, right, whereby it can sort of assign an output into one of let us say 10 different classes, right. So, that is very much possible. So, the output of the perceptron can be modified to such that the perceptron automatically performs multi-class classification. So, this is something that is fairly straightforward to use. So, how do we construct a perceptron, right. So, we sort of realize that perceptron is one of the building blocks of our artificial neural network. So, how do we actually construct a perceptron? It is actually important to note that if you only use a single perceptron in our model, so let us say our model only consists of one perceptron, nothing else, it is actually just a linear model, right, because we have a linear summation of weights times our input values, right. So if you have a linear summation of them, that is basically related to linear regression. The only minor modification is that you put in your net inputs through some kind of a threshold function, right. But if it is only one threshold function, all you are doing is linear classification, right. So we can actually use the linear model module from the scikit-learn package to create a simple perceptron. And the way you do it is from the linear model module you just import the perceptron class, you initiate an object of the perceptron class, and you use the same fit function that we have been using so far with features and your target values, and if you want to make predictions you then put in your new feature here, right, that you want to make predictions on. Apart from the linear model, you can also use the stochastic gradient descent classifier or the stochastic gradient descent regressor also to create or to construct perceptrons. So although we have introduced perceptrons largely for classification tasks, they can also do regression tasks. Okay. Now the key thing to note is that perceptrons are very good at perceptron by itself. So we have not created a network of perceptrons here. A perceptron by itself is very good at classifying linear data sets. So in other words, it is very good at separating out data sets that are linearly separable in nature, so making classifications of them. So to give a sort of visual example, right, so let us say you take the outputs of a simple AND gate, right. So your L1 and L2 are the two input values that you pass through your AND gate, right. So you can think of them as features, right. So L1 is one feature, L2 is another feature. If both features are 1, then the resultant value is 1, but if either of the features are 0, then the resultant value is 0, right. So that is how an AND gate sort of performs. And let us say you want to classify, right. So you want to classify the outputs of your AND gate. So you want to classify instances where the AND gate actually outputs 1 compared to where the AND gate's output is actually 0. So 0 is highlighted by the dark circles here, and and 1 is highlighted by the light circle here, right. Now for a simple perceptron, this is a very simple linearly separable data set. So it will just draw a threshold classification or a decision threshold that probably looks like this, which can clearly separate out your ones from your zeros. So your predicted ones from your predicted zeros. The same thing is possible if we take an output of a simple OR gate. So in the case of an OR gate, as long as either of the inputs are 1, then the output is 1. If both inputs are 0, then the output is 0. So all the perceptron has to do is sort of shift this decision threshold a little bit down, right, and then you can clearly separate out ones from zeros here, right. But if you take an XOR gate, right, so the way the XOR gate works is if either of the inputs are 1, so if either of the inputs are 1, then the output is 1. If both inputs are identical, so if you have 0 0 or 1 1, then the output is 0. So that is the definition of an XOR gate. So if both inputs are identical, then the output is 0. If the inputs are not identical, then the output is non-zero, right. So you basically have predictions of 1 on either sides here and predictions of 0 here, right. But since your perceptron is a linear model now, it cannot create a good enough decision threshold that can separate out all the zeros from all the ones, right. So this is just simply not mathematically possible, right. So this was actually suggested as one of the major drawbacks of the use of perceptrons, and hence although perceptrons were introduced in 1957, a lot of work did not take place on the development of perceptrons because of this demonstration that perceptrons don't really work on non-linear data sets, right. Now one way to overcome this inherent limitation of a perceptron is by basically stacking perceptrons into different layers. Right. So if we take an example here, right, so this could be your x1 x2 inputs similar to all the gate inputs here, right. So we take x1 and x2 as two inputs, we pass them on to two perceptrons here, right, and depending on the outputs of those two perceptrons we then stack one more perceptron on top, which gives the net output, right. And these sort of orange circles here represent some kind of bias terms. The bias terms can be added to either both the inputs in one go or both the inputs separately also. So that is a design choice. Now typically if the bias term is considered to be some kind of an offset kind of a term or a constant term, right. So it sort of feeds in equally to both your inputs here. So you see that the bias is feeding into both the perceptrons here equally, right. And then you have x1 contributions here, x2 contributions here, and same thing you have a bias term here which then contributes to your x1 and x2 here, right. Now if you stack up perceptrons like this, right. So you rely on the predictions of let us say multiple perceptrons in one layer. So you can consider this to be a layer because all of these perceptrons make predictions at the same level at the same time, right. And then there is another perceptron that takes the inputs of these layers and then starts to make predictions. Then we can start introducing nonlinearity, right. And the nonlinearity predominantly comes from the fact that we are using activation functions, right. So the output of this perceptron is subject to this activation function here, same thing with this activation function here. So you have two sort of non-linear outputs that are once again passed through some kind of an activation function here. Yeah, they are linearly summed up and then passed through a non-linear activation function. So we can introduce non-linearity and basically solve this classification problem by stacking perceptrons in layers, right. And if we stack up perceptrons in layers like this, it is basically referred to as a multi-layer perceptron or MLP, right. And MLP is the simplest structural unit or the simplest way to imagine to construct a artificial neural network, right. So an artificial neural network is nothing but a broader collection of MLPs, and it can have various ways by which the neurons are connected within itself, right. Okay, so let's stick to MLPs for now, and let's say you create a multi-layer perceptron, right. Then you may have to think about how do you train the weights, right. So for example, if you take this 2-layer perceptron, so this is layer 1 and this is layer 2, right. So this is the output layer. Layer 1 is what we typically refer to as the hidden layer because these mathematical operations appear underneath within the multi-layer perceptron model itself or the network itself, and their outputs are not directly your output, right. So this is basically your hidden layer, and then you have your input layer here which basically corresponds to two input values, right. So in this architecture we have two different weight terms here for weighting the outputs of these two perceptrons, and we also have two different weight terms that or rather 4 different weight terms because your x2 feeds to both this neuron feeds to both this perceptron and this perceptron, and same thing with your x1, it feeds to both this perceptron and this perceptron. So there are basically 4 weights in this layer and then 2 weights in this layer. So in collection there are about 6 weights, right. So the question is how do we train these weights, right. So this is actually not a very trivial problem. If it was just one single perceptron layer, right, as we saw in the previous example, then we can sort of imagine strategies where we can sort of pass in our errors, basically calculate some kind of gradients with respect to our errors such as gradient descent, and then we could think about evaluating the weights, right. But here because of these nonlinear activation functions, it is actually not trivial to calculate how much will be the gradient of the error as we go down in this ways, right. So training of the weights is something that is not very trivial in the case of multi-layer perceptrons, and this was an unsolved problem for several decades. Okay. And the way to sort of solve this problem of training weights in a multi-layer perceptron is using this mathematical tool called backpropagation, right. So this was actually introduced in 1986, so roughly about 3 decades after the perceptron was introduced by Geoffrey Hinton and co-workers. So you may recollect that Geoffrey Hinton recently got the Nobel Prize for the development of neural networks and so on, right. So Hinton basically proposed the technique of backpropagation to actually calculate the weights, right. And how does it work, right. So basically very simply you do gradient descent cumulatively across the different layers, right, and instead of using a sort of a step function, so step functions are not very differentiable, right. So if you look at this step function here, right. So here the slope is basically 0, here the slope is sort of infinity, and here the slope is 0 again, right. So step functions do not have very good slopes to work with, so you cannot calculate the gradients very easily, but if you change that to a more continuous function such as a sigmoid function, then you can actually calculate the gradients, right. So the idea is to actually calculate the gradients, so the gradients of the loss function or the error with respect to the weights in one layer, and then use that to update the value of the weights, right, and we repeat the same process in layers as we go down in the network, right. So the errors are calculated close to the output, right, and then we calculate gradients in a stepwise fashion and then basically back propagate the errors. So that is why it is called back propagation. How do you actually calculate the gradients? So we very simply use auto differentiation techniques, or mathematically if you want to visualize this is nothing but a chain rule, right. So let us say you have a stack of functions which are basically multiplicative in nature, right, or you have a function of functions, right. So the way you differentiate a function of functions, so if you have f of g of x, for example, you first differentiate f and then you multiply that with the differential of g and then you multiply that with the differential of x and so on, right. So you basically use the chain rule, so you keep differentiating until you go to the final sort of dx kind of variable. So that is basically the technique that we are going to employ in back propagation. And the ways the sort of back propagation is used to update the weights is that the data actually flows through the network twice. So from the input layer you actually do a forward pass or a forward propagation to basically make predictions and calculate the errors, and then you do a back propagation of the gradients of the errors to basically adjust the weights, right. So every time, so you take inputs, you use the existing weights and biases across the layers, and then you make predictions, and then once you make predictions you calculate the error or the loss, right. You calculate the derivative of the loss with respect to the weights and then pass on the errors so that the weights can be adjusted for the next round, right. So you repeat the forward and the backward passes multiple times, the network basically learns or modifies its weights and also the bias terms to make sure that its final loss or final error is minimized, right. So that is in short how multi-layer perceptrons work and also how most modern day artificial neural networks work, right. So just to give some introduction to some of the notations that are used typically in either multi-layer perceptrons or in artificial neural networks. So the lower layers are the layers of the multi-layer perceptron that are closer to the input. So this would for example correspond to a lower layer. Upper layers are those that are closer to the output, right. In general if you have more hidden layers, so more layers between your input and your output, you tend to have a deep network, and you also have a dense network if all the perceptrons connect to every perceptron in the layer above and in the layer below, right. So here you have your input nodes basically. So if your input nodes connect to every perceptron that is available in the next layer, right, then this is corresponding to a dense connection, right. So in the case of the hidden layer, so you see that all the sort of perceptrons here connect to all the perceptrons up and all the inputs in the layer below, right. So this is an example of a dense neural network. Another sort of notation thing to note is that typically you call each perceptron in a given layer as a neuron or a node, right. So these are collection of neurons in a given layer or nodes in a given layer. So generally the inputs we refer to as input nodes, the output, the final output that we actually get, we refer to that as the output node, and then the perceptrons are referred to as either neurons or nodes. Okay. So just to give a visual example of how back propagation works, so let us say you have an sort of initial input here, you pass that on to one of your lower layers, that calculates some kind of an output. So this y of 0 can be an input or an output, right. So basically this is the input of this node here or this neuron here, it gives an output, right, which goes to the second neuron here, which also gives an output which goes to the final neuron here, which gives the final output, right. So the final, based on the final output and based on your target value, you basically calculate your loss, your error. So the loss can be in the case of regression tasks, this can be simple mean absolute error, mean squared error. In the case of classification tasks, this can be a cross entropy loss, for example, right. So once you calculate the loss, you then take the derivative of the loss with respect to the weights and biases, right. So for this neuron to make predictions, right, it would have used some amount of weights and some amount of biases. So based on the gradient of this loss with respect to the weights and biases, you then update this node here, the weights and biases associated with this node, depending on the gradient of the loss function or the loss value with respect to the weights and biases associated with this layer, right. And that is how you sort of update the weights on this node. You do the same process for all the previous layers as well. So after you have evaluated the weight derivatives here, you can simply use the chain rule to also evaluate the derivatives associated with this node here, right, and you use once again those derivatives to update the weights. So you basically do gradient descent here. So you do a gradient descent to update the weights, you do a gradient descent to update the weights here, you then do a gradient descent to obtain the to update the weights here as well, right. So once you have updated all the weights, that is basically a completion of one back propagation pass, right. So initially we did a forward propagation or a forward pass, right, where we used the existing weights and biases to make predictions, and then we calculated a loss. We then took derivatives of the loss with respect to the weights and biases, and then went through the network in a backward direction, updating the weights and biases, right. So once the weights and biases are updated, you then once again take the inputs, make predictions, calculate the loss, calculate the derivative of the loss with respect to the weights and biases, and then update the weights and biases, so on, right. So each time you sort of train a network, you do a forward pass and then you do a backward pass, and you sort of repeat this multiple times, and as you keep repeating this multiple times, the network or the multilayer perceptron tries to minimize the loss value. So it updates the weights and biases such that it sort of reduces the loss value as much as possible. So that is in short how back propagation works. So there is although back propagation is a very good mathematical technique, right, to solve for the weights and biases of a multilayer perceptron or an artificial neural network, there are some mathematical issues also with respect to our back propagation. So for example, if you think about how the weights and biases are actually initialized, right. So we actually require a very good initialization of weights, or basically a very random initialization of weights. If we do not do that, then it really affects how quickly the network actually learns or the network actually updates. Right. So the most trivial example is, let us say you initialize all the weights and biases to 0, right. So all the weights and biases are 0, so then the network will update a 0 value, right, let us say for a classification task, because all the inputs are 0. So if all the inputs are 0, your likelihood of crossing the threshold of your decision function is 0, right, and you would basically have a 0 output, right. So for a binary classification task, let us say you output 0, but then your target value is 1, right, then you want to calculate the derivatives, right, of your loss function, which could be a cross entropy loss, for example here, with respect to your weights and biases, right. But if your weights and biases, the current values are 0, right, then the network will have a hard time trying to figure out how to update the weights and biases. So in other words, if the gradients themselves are 0, right, so the current values of the gradients are 0, then it is hard for the network to update, right. So this is one important sort of constraint or drawback with respect to back propagation. The other sort of important thing to note is that you can, depending on what kind of activation function we use, so the older perceptrons use the step function, which makes it difficult to train the network itself or train the weights and biases. But if you replace that with a sigmoidal function, which sort of looks like this, you can actually perform back propagation, right. But sigmoidal function has a few problems, right. So let us say you are making, so your inputs are close to 0 here. So let us say I have sort of normalized my inputs to between -5 to +5, right. So if your inputs are close to 0, you see that the derivative is actually quite non-zero here, and it is a linear derivative, which implies it gives an option for the network to either update in this direction depending on the sign of the loss function, or in this direction. So in other words, the network will actually update, right. But if you are sort of making if your inputs are feeding in values close to, let's say 4 here or -4 here, you see that the derivatives are almost close to 0 here. So this is sort of saturating behavior of your activation function, and if your derivatives are close to 0, then the network won't update very easily, right. So if the network is not updating, it will take a long time to reduce any residual losses that it has, right. So if you use a sigmoidal function, you have the problem of vanishing gradients, and depending on what kind of loss function you use, you can also have exploding gradients, right. So let us say you sort of use a step function, right. So the step function actually has infinite slope at your decision threshold, so that can lead to exploding gradients as well, right. So the choice of activation function is very important for backpropagation to actually work, right. So backpropagation sort of solved a key mathematical challenge on how you train a multilayer perceptron, but it has two sort of main shortcomings. So one is it requires good initialization of weights, and the other is it requires a good activation function, right. So because of these two problems, although backpropagation as a technique was introduced in the 1980s, it took about 1.5 to 2 decades for these problems to be systematically solved and for neural networks to become more mainstream, for multilayer perceptrons or neural networks to become more mainstream. So how do we initialize the weights, right, in modern multilayer perceptrons or artificial neural networks? So the common scheme that is actually used is was introduced by Gloro and He in the 1990s, and the way this sort of initialization works is that you pick a set of initial weights randomly from a normal distribution, right. So you define some kind of a scale for your normal distribution that could be -1 to +1 for example, and you create a normal distribution and you pick weights randomly, you sample weights randomly, and those sampled weights are the ones that will be your initial weights, right. But the key thing to note, I mean the first point may sound like very trivial, but the key thing to note is the second point, right, which is that the variance of this normal distribution, right, was said to depend on the width of your adjacent layers, right. So let us say you have a neural network architecture, your current layer has about 10 nodes, so your width of your current layer is 10, right, and if one of the layers next to you, so above you or below you, has 20 nodes, right, and let us say the layer above you has only 5 nodes, right, then the variance of your distribution not only depends on how wide your layer is, but also how wide your adjacent layers are. So your one of your adjacent layers is fairly wide compared to your width, and one of the layers has a smaller width. So the middle layer has width of 10, the forward layer has a width of 5, and the backward layer has a width of 20, right. So depending on the width of your adjacent layers as well, you choose some kind of an intermediate variance for picking the weights of for picking the initial weights of your middle layer of the layer with 10 nodes, right. So as I mentioned, width corresponds to the number of neurons in a given layer. So basically if you pick the variance keeping into account what is the width of your adjacent layers, you basically try to maintain similar variance of gradients across multiple layers, right. So in other words, the gradients themselves vary in a similar fashion, right, across the different layers, thus sort of solving the problem of either exploding gradients or saturating gradients, at least in the initial few iterations, right. So Gloro and He initialization is often used in multilayer perceptrons in the modern era. The other sort of important advance that was made was in terms of activation functions, and the sort of major advances happened around the 2010s or so, but advances started coming in the first decade of 2000s as well, right. And there are various there is now a whole zoo of activation functions that we can sort of choose from. Right. So the step function is what we saw before, so this was introduced in the perceptrons in the 1950s, followed by the sigmoid function that was used by Geoffrey Hinton, right. We can also think of hyperbolic tan function, right, which also has a saturating gradient problem here and here, but it at least has a larger linear region here, and the other more popular activation function is what is referred to as the ReLU function. Right. So ReLU stands for rectified linear unit. So you have basically the way the activation function works is if your input values the net sum of your input values are less than 0, then the function sort of outputs a 0 value, but if the net value is positive, then it outputs a linearly sloped value, right. So the actual output depends on the net input value. So it does not just output 1, it outputs some kind of a linear function of your weighted input, right. So this is an example of ReLU. For all of these functions you can sort of visualize the corresponding derivatives here, right. So how the derivatives are actually varying here, and you see that for the sort of tan H function you have an exploding gradient at 0 here, right. One of the key takeaway messages with respect to ReLU is that since it has a non-saturating behavior here, so basically your gradient your slope here is constant, right. So the actual value of the gradient will depend on your inputs as well. So the higher the inputs, the higher the value of your gradient as well, right, and the more the network will actually update. So the more important your inputs become, the more your network will adjust its weights and biases for that particular node, and the better its predictions will actually become, right. So ReLU was found to be much more useful, much more useful for training multilayer perceptrons. So in other words, ReLU accelerated the way sort of artificial neural networks learnt from their target values, from their loss values. If you think about the number of iterations, right, so number of forward and backward passes that a neural network will require to learn a certain task, if you use a ReLU activation function, the number of passes that it required was significantly fewer compared to if you used, let us say, a sigmoidal function or a tan hyperbolic function, right. So as a result, ReLU is one of the most popular activation functions that is used in modern day neural networks. It is also quick to compute because once again your slope is either 0 or a constant value, so you just multiply that with whatever is the inputs, and then it also has a non-saturating gradient for values greater than 0, right. But ReLU is not perfect, so you see that at if your input values are less than 0, so this is some kind of a normalized input, right. So if your input values are less than 0, then ReLU gives a 0 gradient, right. So in other words the network does not update. So once the inputs go below a certain threshold, then the network does not update at all, and basically the sort of neurons become dead in some sense. And this may affect how the model actually sort of learns. So there have been activation functions that have been introduced to mitigate this problem of saturating gradients for low values of inputs, for low values of x, and examples are SILU here, which has a small sort of non-zero gradient here, for example, right. You have a leaky ReLU where you have a sort of a linear leak. So the slopes here are also linear, but they are significantly smaller compared to the slopes in the positive region here. And you also have the ELU activation function, so which is the exponential, so the leaky part here is exponentially dependent. So initially you still have a fairly large gradient, but then the gradient sort of saturates as the inputs become more and more negative, right. So there are various possible activation functions that we can use. There is also a SELU or SELU activation function that I have not indicated in the graphs here. So although there are lots of different activation functions, ReLU still turns out to be one of the most commonly used activation function. Okay, so how do these machine learning perceptrons work for regression? So what type of features or hyperparameters do we have to keep in mind, right? So for example, if you think about for regression tasks, we have to worry about number of input neurons as well. So if you think about an MNIST data set, then the total number of features that we have is about 784, so one value per pixel of your image, and the number of input neurons is typically 1 per input feature. So if you have 784 input features that characterizes an image, then your input node, your input layer will also have 784 input neurons. The number of hidden layers, so it typically depends on the problem. We can use anywhere between 1 to 5. So the idea is to always start with fewer layers and then increase that dependent on the problem. Number of neurons per hidden layer, this also depends on the problem. So good exercise is to start with fewer numbers such as 10 and then increase the number. But the general strategy is the number of neurons is almost always fixed. This is a hyperparameter that's fixed first and then the number of hidden layers is changed, right. So there are various studies that have sort of specified how a width of a layer affects the accuracy of your neural network compared to the number of hidden layers. So depending on all that, the general sort of procedure is to fix the number of neurons per hidden layer first. That is a hyperparameter that we would tune first and then we would sort of worry about the number of hidden layers. The number of output neurons, this again depends on the problem of prediction. So if it is a very simple regression task and we are predicting one value, so let us say that is a scalar quantity, right, something like band gap of a material, then that could be just 1. So the output neuron will just be 1 which predicts one single floating point value, right. But let us say for the same material we want to predict multiple things. So we want to predict formation energy, we want to predict Young's modulus and we want to predict band gaps. All three are again regression tasks. So there are 3 different floating point values that we need to predict, then we would need to have 3 output neurons, right. The activation function typically is a ReLU, it can also be SeLU, right. And the output function, the output activation itself, or the activation function for the output neuron. For regression tasks we typically do not need an activation function, but if necessary, so if you want to make, if you want to only worry about positive outputs or make sure that your outputs are bounded, right, bounded to a certain maximum or a minimum value, then you can certainly use some kind of an activation function. But general advice is not to use any kind of activation functions for a regression task. And the loss function itself for regression tasks, so it is either mean squared error or mean absolute error. You can also use a Huber loss function which gives you an ability to mix how much of mean squared error you want in your loss function and how much of mean absolute error you want in your loss function. So these are all sort of hyperparameters that we need to worry about when we use multilayer perceptrons for regression tasks. So similarly, if you use multilayer perceptrons for classification tasks, you will have to worry about all the hyperparameters that were mentioned in the previous slide for regression tasks as well. The one major change is the number of output neurons. So if it is a binary classification, then we just use one neuron. If it is a multi-label classification, then we have to use 1 per label, and if it is multi-class, then we have to use 1 per class, right. So multi-labels could be is the number itself, is the number big or small, is the number odd or even, something like that. So this was the case in our classification MNIST classification task. Class could be classifying our output into one of different classes, so 0 to all the way to 9, right. So we can use so the number of output neurons in any classification task will depend on how many different ways we want to actually classify our inputs, right. And in contrast to regression models, for classification models we will almost always use we will almost always use activation functions in the output layer, right. So in the case of binary classification or even multi-label classification, we will use a logistic function, right. In the case of multi-class classification, we will use a softmax function, right. So basically in the case of multi-class classification, we use a softmax function because it can sort of evaluate the probability for the different classes and then choose or sort of make a prediction on one class that maximizes the probability. So that is why we use softmax. For multi-label classification, for each labels we basically use a logistic activation function, so which would give a value of either 1 or 0. So whether your input has a value corresponding to that label or not, right. And typically the loss function is cross entropy. This is almost always used in used by neural networks for classification tasks, right. Okay. and so we looked at the basics of machine multi-layer perceptrons. We looked at their hyperparameters as well. Now let's also look up the algorithm by which these multi-layer perceptrons are typically fit, right. We typically don't use a standard gradient descent such as batch gradient descent or stochastic gradient descent, because these algorithms oscillate too much, so for these multi-layer perceptrons to converge. So the algorithm that we typically use is what is referred to as momentum optimization, and this was introduced back in the 60s, right. So what the main idea behind momentum optimization is that it continues to do gradient descent, right, but on velocities rather than displacement. So it basically does gradient descent on the second derivative of your loss function rather than the first derivative of the loss function, right. So the gradient computes what is referred to as acceleration rather than the velocity itself. So if you have displacements of your weights and if you take gradients of that and then change those gradients, right, so that is equivalent to changing the velocity, but if you take the gradients on the velocities and then update the velocities, right, at each iteration, then that's basically computing some kind of acceleration, adding that acceleration so that velocities get updated instead of computing velocities and adding those velocities so that you get some net displacements, right. So it's basically doing one more level of or updating weights one level below in terms of their gradients. One can also think about this in terms of curvatures and slopes, right. So if you update slopes for a given loss function, then that is our simple gradient descent, but if you sort of think about updating curvatures, then that is momentum optimization. So how does momentum optimization practically work? So it basically adds changes to weights through some kind of a damping function or a friction function, right, and momentum optimization is really useful because whenever we sort of have flat kind of valleys, right, stochastic gradient descent can take a long time to roll down such flat valleys, but momentum optimization can help you roll down those valleys faster, right. So basically if it identifies that it's a fairly flat slope, then the amount of acceleration that will be added will be higher, so your weights and biases will get displaced by a larger extent compared to if you just use stochastic gradient descent. Momentum optimization was the sort of go-to algorithm till the early 2000s until Adam came in and changed sort of changed the scenario. So Adam was basically developed around the mid 2010s, so 2014, and Adam basically refers to adaptive momentum estimation. So basically how does Adam work? So it once again includes some kind of curvature effects to the gradients, and it accumulates these sort of gradients over a certain number of steps. So in other words, Adam sort of remembers some amount of history of how your gradients were actually varying or how your curvature was actually varying, and this history helps it to determine what should be the net displacements of your weights or net displacements of your weights and biases. So it can use this curvature information to tune the learning rate. So remember that learning rate is how the weights and biases actually get updated. So you can actually use this curvature effects to tune the learning rate to be higher along steeper gradients and lower along shallower gradients. So higher along steeper gradients because you are far away from the minimum and you want to reach the minimum quickly, and low along shallower gradients because you don't want to miss the minimum and cause unnecessary oscillation. Adam is a very popular optimizer, so almost always it's the default optimizer that's used in most artificial neural network architectures that are used in the modern era, right. Another variant of Adam that is quite popular is basically in Adam, but this works very similarly to Adam as well. So if you are thinking about so to give an analogy, right, so if you are fitting classical machine learning models, almost always you would use stochastic gradient descent or batch gradient descent as your optimization algorithm. If you are using artificial neural networks, right, then by default or almost always you will use the Adam optimizer or the Adam algorithm to fit your weights and biases or to train your weights and biases. Okay. Just to reiterate on some of the important hyperparameters that's relevant for neural networks apart from what I had suggested before in the case of regression and classification tasks. So the number of hidden layers is a very important hyperparameter. In general, deep networks are good for complex problems. So to give an example, right, so let's say you want to recognize the image of a forest, right. So it's almost always better to decompose the an input image of a forest into a collection of trees first. So you first start trying to identify collection of trees, and for each tree you also try to collect, identify a collection of branches, and for each branch you also try to collect identify a bunch of leaves, right. So while learning whatever is the image of forest that you are given, you want your model to first learn the forest first, or take a look at the forest first, decompose that into trees, decompose that into branches, and then decompose that into leaves, right. So that when you are introduce, or if you want the model to generate, or if you are introducing newer let's say images and asking the model to classify whether that's a forest or not, the model will first learn to recognize leaves, then put together leaves and form branches, then put together branches to form trees, and then see if the trees can be put together to form a forest, right. So this type of learning, so this type of decomposing your overall input into multiple smaller features of your input is referred to as hierarchical learning. So forest is the most highest object that you want to recognize, trees are one level below that of forest, branches are one level below, and leaves are the simplest objects, right, that you want to recognize or that you want to learn, right. So if you want to train on forests, right, your neural network should be able to do this kind of hierarchical decomposition, right. So the deeper your neural network is, the more it can do this kind of hierarchical decomposition, right, and the shallower it is, so the fewer layers you have, it won't be able to do all of this decomposition. So maybe it will stop once it does forest to tree decomposition, it will stop there simply because the model is not complex enough to do even finer decomposition into branches and leaves, right. So a general sort of piece of advice here is that the number of hidden layers, almost always you sort of start with 1 or 2 and then you keep increasing to see how the model is actually performing. Number of neurons per hidden layer is once again a very important hyperparameter, and this is a hyperparameter that we typically tune ahead of the number of hidden layers itself, right. So in the olden days, I mean by old I mean in the early 2000s and so on, neural networks almost always used pyramidal structure. So the lower layers, so the layers that are close to the input nodes, right, they would have more neurons, and as you get closer and closer to the output, you will have fewer and fewer neurons. So if you sort of visualize the neural network from down to up, where down is the input layer and up is the output layer, it sort of looks like a pyramid, right. So this was referred to as a pyramidal structure, and the pyramidal structure is fairly an old way of designing neural networks. In the modern era, we typically want so we want to fix the number of neurons in the input layer to the input data dimension. So that's something that we want to we want to keep the same, but for all the hidden layers after that. So let's say you have 4 hidden layers between the input and the output layer, you sort of want to fix the same number of neurons for all the hidden layers, right. And this basically has to do with the fact that we don't want to lose complexity as we go from one hidden layer to another hidden layer. So that's the basic idea behind this. So we basically try to fix a number for all the hidden layers and keep that number constant across the different hidden layers, right. So let's say your input layer dimension is about 784 for your MNIST data set. Your output is 1, let's say you want to classify whether it's a 5 or not 5, and let's say you have 2 hidden layers, maybe in the hidden layers you can have 30 nodes each or 30 neurons each, right. So typically the idea is to fix the number of neurons per hidden layer and then vary the number of hidden layers, right. One strategy that's also used, so I mentioned before that you try to start off with lower number of hidden layers and then increase the number of hidden layers. One other strategy that people also follow is they try to take a very large number of hidden layers and neurons per layer than what is required for the problem, and then they try to reduce the model architecture by some kind of regularization right. So they try to identify which neurons are active, which neurons are not active, which layers are adding information, which layers are not adding information, and then they try to cut down the model, right. So this is another approach that one could take to design a neural network. The only caveat is that this strategy can have a tendency to overfit, and if you are not careful enough with your regularization, you may actually miss the extent of overfitting that the model is actually doing. Okay. Another important hyperparameter to keep in mind, especially in neural networks, is learning rate. So imagine, remember that learning rate is how you are updating your weights and biases in your model. We introduced learning rates right when we introduced simple linear regressions, right. And just as with linear regressions, depending on the value of the learning rate, your model can either not converge properly, so take very long to converge, or it can actually diverge, it can oscillate and diverge, right. So if your learning rate is way too high, the model can actually diverges. If it is too small, the model is not learning properly. If it is sort of too high, also the model is not learning properly, its losses are sort of plateauing. But if your learning rate is sort of just right, then you can your model actually converges to a reasonably good value. One approach that people typically take for learning rates is to do what is referred to as learning rate scheduling. So in the initial few iterations of the model, you try to have fairly large learning rates so that you quickly reduce your loss, and then once you reach a reasonable value of loss, then you shift your learning rate to you sort of shift your learning rate to this value here, a lower value, and then the model sort of converges slightly better compared to if you used the optimal learning rate right from the beginning, right. So learning rate is once again a very important hyperparameter, and once again this is hyperparameter that we need to tune fairly early in our training exercise itself, and we have to be very careful in how we are tuning the learning rate, so that we don't use a lot of compute power, as well as making sure that the model doesn't diverge. One sort of rule of thumb is to always vary the learning rate by 1 or 2 orders of magnitude and seeing how that affects the model performance, right. Another important hyperparameter, and this sort of gets swept under the carpet a little bit, is the number of steps in an epoch, or how do you actually split your data into batches, right. So let's say you have a batch of let's say you have 100 data points and you create a batch of 10 data points. So you basically create 10 batches. Then the number of steps in an epoch is basically the number of batches you have. So if you have 10 batches, then your model will do 10 passes, so 10 forward and 10 backward passes in one epoch, and it will complete training within that epoch. So the idea behind this definition is that one epoch is when the model has seen its training set completely, right, all the training data points completely, and the model generally becomes better the more epochs that you actually train the model, right, because it is seeing the training data multiple times, it has more abilities to sort of reduce its losses, reduce its errors, and the model is trying to become better, right. Now the way you actually split your training data set into batches, so in other words how many batches you actually create in your training data set, that is actually a very important hyperparameter, and it really affects how quickly your model actually learns and how easy it is to train your model. Because if you create more batches, then you can sort of train the model in parallel along those different batches. So in other words, your model becomes faster to train, but in general more batches also means that the amount of memory that you require will be higher, right. So that is a very important sort of computational hyperparameter. It can also affect accuracies to some extent, right. So if you to sort of think more about the computational aspects, right. So if you had a data point of if you had a data set of 100 data points, and if you only created one batch, right, then the model has to basically do 100 steps in one epoch, right. So it basically has to see all the 100 data points in a sequential fashion, right. So that takes a lot more time compared to if you create 10 batches, then the model sees batches of 10 data points at any given point of time, and it only needs 10 steps to complete in an epoch. So the model generally becomes faster. So the number of batches that you actually create may depend on what kind of computational resources you have, right. So the more resources you have, typically the more number of batches you would want to create, but also keep in mind more batches means higher memory load. Okay. Now let us get to regularization. So neural networks are very complex models, even more complex than our ensemble models, right, which means that they tend to overfit data very easily. So in other words, neural nets are neural networks and multi-layer perceptrons are models with very high variance, right. So it is important for us to introduce as much bias as possible so that the model does not overfit and we get a good model, right. There are two ways by which you can actually regularize your neural networks. So first is referred to as batch normalization. So what you basically do is, so for every batch of data that the model actually trains, you sort of learn the weights and biases. So you use gradient descent, use the Adam optimizer for example to update your weights and biases, but after one batch of data is done, you basically normalize the weights and biases to be within a certain given interval, right. So this makes sure that weights and also biases for a given layer and or for a given node do not explode. So you do not get weights of 1000 for one node and then 0 for another node, right. So your weights are always distributed in a narrow range, which which almost always ensures that your model is trying to use as many neurons as possible, right, in making its predictions. So generally if a model uses too few neurons to make a prediction, so if you pass in some inputs and then let us say only one neuron per layer gets activated for the final prediction to be made, then that's an example, that's almost always an example of an overfit model, right. So the model will not be able to make extrapolations or deal with data that it has not seen before very well, right. So if the model uses several neurons to make a prediction, then there is a high chance that the model is actually learnt things across the several neurons, or each neuron is contributing to some extent to the final predictions, and the model becomes better at making those predictions. So batch normalization basically makes sure that no one neuron or no one layer becomes too dominant, right, in the neural network architecture. We can also use L1 or L2 regularization, but it is not very popular. This regularization works very similarly to how we added them to linear regression as well. So here the magnitude of weights is your penalty term. So here the magnitude of the weights is your penalty term. So you want to reduce the magnitude on the weights as much as possible, right. The third way to sort of regularize your neural network is to introduce what is referred to as dropout. So during training you basically select a random set of layers or neurons to be ignored. So for each batch of data only certain number of neurons get trained, right. So they see the data and then they get trained while the other neurons are not explicitly trained. Right. So what basically happens is once we sort of repeat this exercise for all the different batches, for calculating the final training error, so error on the entire training data set, we do evaluations using the entire neural network architecture and then we evaluate the training errors, right. So if we do that, we basically ensure that each set of neurons that we are including during our training actually contributes. So let us say for the first batch of 10 data points, your first half of your neural network contributed to learning. In the second batch of your data points, let us say your second half of your neural network contributed to learning. Then if both neurons are not contributing together, right, then you can have an instance of sort of overfitting. But basically what dropout ensures that you always have several neurons or several fractions of neurons contributing to your final predictions, and hence it leads to more sort of regularized model. So dropout is another very important tactic that is commonly used, and the final tactic that is used is again the very popular early stopping, right. So we basically give a large enough number of epochs and then we try to terminate the model when it reaches the lowest value in its validation error, right. So with respect to regularization, batch normalization and early stopping are very popular strategies that are used in most modern day neural networks. L1 L2 regularization is not very common. Dropouts are a strategy that people use in very dense neural networks, particularly on training with very sparse data sets. So just to give a set of general guidelines, right. So deep neural networks are quite good at dealing with complex data sets. They have a hierarchical learning that is inbuilt. They have inbuilt non-linearity and they are quite versatile as well. and they are but they are prone to overfitting. They normally require a lot of data to train to become stable models, and they can be slow to train as well, right. So there are several ways that we can computationally use the or computationally optimize neural networks. One is to saving the right models and using what is referred to as a callback feature to get the best possible model. And second is to optimize memory. So we have to reduce the memory load as much as possible, especially during testing, during the production part of neural networks. And the third is the large number of hyperparameters, right. So the neural networks typically have several hundreds of hyperparameters, so we cannot do a grid search scan all the time. So we have to scan randomly and then optimize those hyperparameters. And since neural networks are prone to overfitting, regularization is very important. So we need regularization to ensure that the fit is optimal. So how to build neural networks? This we will see as a demonstration in the next lecture. So we will use both Keras and TensorFlow. This is sort of more recent set of Python packages. They have very good documentation. The coding is fairly simpler. But PyTorch, we will also use PyTorch to build neural networks. PyTorch is once again a very popular Python package to build neural networks, and many of the codes that are specific to materials are written in PyTorch. So we will see examples of building neural networks with both these frameworks in the next class. So with that, I thank you once again for joining today's lecture. I will see you all in the next one.